Last time we alluded to the fact that we can classify irreducible root systems through connected Dynkin diagrams, and so that's what we're going to be aiming to do today, is find a way to talk about every possible Dynkin diagram here. And we start with a theorem that we're going to be working on, I think, today, which states if phi is an irreducible root system, of rank L, its Dynkin diagram is one of the following. And so what are all our Dynkin diagrams here? We have AL for L being at least 1. And it's just a bunch of nodes up until connected in a straight line. And then, of course, we're going to have L nodes total. There's BL for L at least 2, which has a bunch of, which looks like a up until the end, where we have a double path connected outwards. We have CL for L at least 3, which is the same once again, except this time the very last connection is pointing in the opposite direction. We have DL, which once again has to be at least ordered at least 4. Once again looks just like A, except at the end we have the second branch here. And then we have E, which comes in 3 forms. We have E6. There's also, I guess I should see, these are all numbered in a way that matters, I think. They're all 1, 2, 3 through L. And in the case of D here, we have L minus 2, and then L minus 1 being one of these, and L being the other. I guess it'd be more symmetric to have it like this. We then have the E's. E6 looks like this, with this being node 2 and 1, 3, 4, 5, 6. We have E7 with 7 nodes, which is the same thing, except now connected to 6 is 7. And we also have E8, which you'll never believe this, but it's just 7 on 2, 8. There we go. And then we have 2 extra ones beyond that. We have F4, which is this one we saw earlier, with a double connection in the middle pointing whatever direction you want. 1, 2, 3, 4. And G2 with nodes 1 and 2 and pointing one direction, and this is the only triple connection it looks like we'll see. And these restrictions, it's worth noting, is just to avoid duplication. Otherwise, in any case, L is 1 is going to give you A1, which is just a single node. C2 will also look like B2, and L only really starts to make sense at 3, in which case it looks like A1. So L has to be in the case of D. So they also give the Cartan matrices for all of these. I will just say this one is -1, -3, and in this case it's -1 on the side it's pointing to, -3 and negative number of branches on the other side. And the rest you should be able to do yourself, otherwise we're going to be here all day and we're not going to see much from these matrices themselves. And so we can also see, we see from the Cartan matrices the only need for the Dynkin diagram is to differentiate BL and CL, because like the structure of all theory otherwise is unique. It's just this B2 C2 is ambiguous. Which have the same coxeter graph and different numbers of, the same number of roots total obviously for the same L, but the distribution of those roots among short and long is going to be different. And the proof. First, we want to classify the coxeter graphs with understanding the possible Dynkin diagrams, from that being pretty straightforward. Applying just Euclidean geometry to finite sets of vectors with the pairwise angles from the graph determined by the coxeter graph, given the table we have seen before. And since we're just using short and long, and we're going to be assuming that these are unit vectors. And we're going to only make a certain set of assumptions, which I'm trying to load. We're having problems here. Assumption that E is a Euclidean space of some dimension U being consisting of E1 through En is a set of linearly independent unit vectors with the form of each pair being negative, being non-positive, and 4 times the square of EI and EJ of their form being 0, 1, 2, or 3. In this case, we call our set admissible. For example, these can be the elements of a base of a root system scaled down to the unit. So we attach a graph lambda, no, that's gamma to U, as we did for the simple roots with vertices I and j joined by this 4EI EJ squared edges. Now we want all possible graphs of this sort. Of all possible graphs of admissible sets, which will then thus include our coxeter graphs. Okay. So, step 1. If we discard some of the EIs, the remaining set is still admissible with corresponding graph obtained from gamma by dropping the relevant vertices and edges. That's assuming we're dropping multiple vertices here, multiple elements. And we just drop every vertex that belonged to one of the elements we discarded and every edge connected to one of the vertices we discarded. And this is obvious. Number 2, the number of pairs of vertices of lambda connected by edges, so essentially a non-zero number of edges, is less than n, being the size of our u, remember? And we are going to prove this. So we're going to set epsilon to be the sum of epsilon I for I is 1 to n. since our epsilon is linearly independent, since our collection of epsilon I is linearly independent, epsilon is non-zero. So we have that the pair of epsilon with itself is positive, is n plus 2, the sum of I less than j, ei, ej. So let I and j be distinct. Pick a pair of distinct indices with their form being non-zero. So I and j are joined. And then for ei, ej squared is non-zero, 1, 2, or 3. So 2 times ei, so 2 times the form of ei and e epsilon ej is at most -1. I'd be calling these e's, they're epsilons. So the number of edges, thus the number of edges, the number of not edges of joined pairs is at most n-1. Which has an immediate obvious consequence that lambda does not contain cycles. So it'd be a cycle would be the graph. I guess would be is more clear in this sense. The graph lambda prime of an admissible subset u prime of u, not u of itself, with lambda prime then violating our previous result for n equals the cardinality of our lambda prime. U prime, not lambda prime. Part number 4. Each vertex has at most 3 edges that connect to it. How do we know this? Say epsilon is an element of our U with etas, eta I from 1 to k. The vectors in U connected to E i.e. The bracket of epsilon and eta I is going to be negative, with eta and each epsilon distinct, all distinct. From part 3, no two epsilon I can be connected. So the bracket of eta I and eta j is 0 for all distinct I and j, as u is linearly independent. Some epsilon 0 in the span of epsilon and these etas is orthogonal to all of the etas, so that would make it, that would give it a non-zero bracket with non-zero form with eta, epsilon. Pay attention more to what I'm writing than what I'm saying. Now, as we have that epsilon is the sum of the form of epsilon on each eta I scaled up by scaling each eta I, giving us that 1 is the form of epsilon with itself, is the sum of the sum is from 0 to rk, and so this one is as well from 0 to k of epsilon with each eta I squared, so that the sum from 1 to k of epsilon with each eta I squared is less than 1. So multiplying it by 4, we get that the sum of 4 epsilon eta I squared is less than 4. With reminder that each 4 epsilon eta I squared, the number of edges from epsilon to eta I in our graph. And we have a consequence of this. The only connected graph of an admissible set with a triple edge is the graph of two vertices connected triply, which is pretty obvious given what we have so far. Number 6 is, let's say, a subcollection of our admissible set from 1 to k inside of U generate a subgraph of the form A1, as we saw, of just a straight chain. In lambda, Then if u prime is equal to u minus this collection, and then we add epsilon back in, for epsilon being the sum of our epsilon I, then u prime is admissible. All right. So u prime is clearly linearly independent by our hypothesis. Two times the form of epsilon I with its neighbor epsilon I plus 1 is -1. So the form of the epsilon with itself is k plus the sum for I less than j of epsilon I with epsilon j is equal to k minus 1, which is obviously 1. So epsilon is a unit vector. Then we have that any eta in epsilon minus this e to the I from 1 to k can be connected to at most one of the epsilon i's, so that the form of eta with epsilon is 0, or else the form of eta with epsilon is the form of eta with epsilon ei for each I. Either way, 4 times the number of connections between eta and epsilon is a valid amount. Alright, just look ahead here. Yeah, there's 10 parts to this. So we're a little over halfway done. Just want to check on how long it's been. Alright, that looks alright. So 7. Our gamma does not contain subgraphs either this, which is a single chain connecting to a double chain on either end. We don't have this same double chain connecting to a single chain. So single chain cannot have a double connection or a branch on both ends, essentially, is what this is saying. So like we have that every connection is a single, double, or triple, and we have here that a single chain. So aside from, and we have that each vertex has most 3 connections. So if we're outside of the triple connection case, every connection is either in a chain, either as an edge or a center, or is connected to a double chain on either end, or a branch. And this is saying that a single chain can't have those on both ends. Okay. So our proof assume otherwise. And then by our previous result, we can generate the following graphs. Essentially, we can shrink down a chain to one node, as we saw. So this case is going to give us this one, with the middle having 4 vertices for 4 edges. And I think in all these cases it's going to have 4 edges in the middle. Which means, and these are clearly inadmissible, which means the above graphs are also inadmissible. So in number 8, any connected graph lambda of an admissible set has one of the following. Yeah, first case is another simple chain. First case is a pair of simple chains connected by a double chain. Third case is, as we saw, one of the following forms. So I think this is all of our cases just without the additional constraints from before. In the second case, we're labeling these eta 1 through eta p, and then in the other direction, epsilon 1 to epsilon p, in the other direction, eta 1 through eta q. And then we have a fourth version, which is epsilon 1 to epsilon 2, numbering all the way into epsilon p minus 1 to a branching point C, which connects to eta p minus 1 and forms a single chain all the way up to eta 1. And then we have a third branch of eta. Now this is R1. These don't have to have the same lengths. Down to eta 1. And our proof is that only this graph can have a triple edge by number 5. A graph can only have one double edge or else it would have a subgraph double edge into like this, which we know is invalid. and which we saw, and a graph with a double edge cannot contain a node, which is a branching point. Which means the only case of double edge is the second case, and the only case of the branch is the fourth. Oh, no, we don't have that yet, so. So only the second case can have a double edge. So, like I said before, there's essentially the string in the first case is kind of the base case, and there's the only ways that we can have like something fancier going on is by having a double edge, a triple edge, or a branch. And we know there's only one way you can have a double or triple edge so far by these the two middle cases. And now we're going to see you can only have one case with a branch. So let sigma only have single edges. If it doesn't have a node, it is a simple chain, the first case, as it has no cycles. It can have at most one node. Giving the last case. And so these are our only possibilities. Number 9. The only connected graph of type 2 with a double edge is the coxeter graph F4, which, as we recall, is this one. So it has to have exactly one connection on both sides, or B to the N, C to the N, which are, they're different as Dynkin diagrams, but they're the same as coxeter from before, which is a simple chain connecting up to a single double edge right at the very end. And the proof. We're going to set epsilon to be the sum of 1 through p of I epsilon I, and eta to be the sum of I through 1 q of I eta I, which we recall eta and epsilon are the two different sides on the double chain as we see in the diagram up above. By hypothesis, we have that 2 times adjacent elements on either side of the chain is -1, 2 times eta I plus 1, and all others are orthogonal. This is our assumption. So the form of epsilon with itself is the sum from 1 to p of I squared minus the sum of I1 to p minus 1 of I plus 1 is equal to p times p plus 1 over 2. And similarly, the form of eta with itself is q plus 1 over 2. Since 4 times the number of edges where these two meet up is by assumption 2, we have that epsilon and eta squared is equal to p squared q squared times epsilon p on n q on eta squared. Eta q squared, I am struggling, which is p squared q squared over 2 by the Schwarz inequality. We have that the form of epsilon and eta squared is less than the form of epsilon with epsilon and eta with eta, or that p squared q squared over 2 is less than p times p plus 1 q times q plus 1 over 4. So p minus 1 times q minus 1 is less than 2. So p and q are both 2, which is f4, or 1 of p and q is 1, giving us dl and our BNCN. I forgot both the name of the case and how we're indexing it. And lastly, number 10. So if we look back up at our cases here, we know every case of the first and third type trivially. We now know every type of the second, every coxeter graph of the second type. So now all we need is every coxeter graph of the fourth type. And which leads us to number 10, which is the only connected lambda of type 4 is d to the n, which is a simple chain connecting up to a branch with one node on each, or e to the n, which is a branch on the third node connecting to a bunch of others, for n being 6, 7, or 8. And the proof is, once again, we're going to let epsilon be the sum of I epsilon I, eta be the sum of I eta I, and wait, which one's eta? I think this is, so we have these three, and they're set up in the same way as before, just in the three cases now. As before, these are mutually orthogonal, linearly independent vectors, with the branching node C not in their span. By case 4, we get the sum of cosine squared theta I is less than 1 for theta 1, theta 2, theta 3 being in no particular order the angles. Being the angles is a particular order of psi, and each of these 3. As in 9, with p minus 1 instead of p, we get that epsilon, the form of epsilon with itself is p minus 1 over 2, with similar results for the other two. And thus we get that cosine squared theta 1 for epsilon is equal to epsilon, the form of epsilon and c squared over the form of epsilon with itself. Similarly for the other two, the form of c with itself is equal to p minus 1 squared times the form of epsilon of p minus 1 and c squared over the form of epsilon with itself, which is equal to 1/4 of, this top part is 2p minus 1 squared over p to the p minus 1, which is p minus 1 over 2p, which is 1/2 of 1 minus 1 over p, with again similar for theta 2 and theta 3. Thus we get that 1/2 of 1 minus 1 over p plus 1 minus 1 over q plus 1 minus 1 over r is at most 1, such which we can rework through a bunch of math that we don't want to do into 1 over p plus 1 over q plus 1 over r being at most 1, being at least 1. Changing labels. By swapping labels around, assume, without loss of generality, that 1 over p is smaller than 1 over q is smaller than 1 over r, or is not greater than. Which is actually going to be less than or equal to 1/2 and if any of PQR is 1, we get just case AN. Thus, we have that three over 2 is less than or equal to 3 over r, which is greater than 1. So r has to be 2. So that 1 over p plus 1 over q is at least 1/2. So that 2 over q is at least 1/2. So q is 2 or 3. If q is 3, then 1 over p is greater than 1 over 6. So p is obviously going to be less than 6. So we get that all triples are the form P2, 2 is dn, 3, 3, 2 is E6, 4, 3, 2 is E7, and 5, 3, 2 is E8, where these are just PQR. And this is the end of our proof, and so we see that the graphs we list are all possible in Euclidean space are the coxeter graphs of A through G. And we have also seen that aside from B and C, the Dynkin diagram is uniquely determined by the coxeter graph, and in the case of B and C, those are the two options, and so we are done with our classification. And then we're done with our video, I guess.